is one of our lockdown lectures, and our speaker today is David Wood. He is the Discovery Manager for Zambia for Anglo American. He has spent time living in Australia, Zambia, Chile and Canada, where his main focus has been base metal exploration. Dave is currently living in Zambia, although not right at this moment, for a second time, and he's focused on discovery of sediment-hosted copper deposits in the Central African Copperbelt. And that's what he's going to be talking about today. So over to you, Dave.
Thank you very much, Nolene, and thank you to the GSSA for the opportunity to speak today. Very happy to be here. So first I'll start by acknowledging on the title page here, there's a number of co-producers of this work. I'd like to acknowledge everyone who was involved in the work, which is from some time ago. So for some people, this might be, you might have heard parts of it before. For some people, it will be new, but it's certainly recent to the copper belt in terms of observations and interpretations. Particularly like to acknowledge First Quantum for permitting me to speak on this topic today. This work was conducted when I was with First Quantum back in 2010 through 2015. And they provided a platform for all of the collaboration to occur. So big acknowledgement to them. And I'd also like just to acknowledge former colleague and good friend James Wale, who was the exploration manager from Kansanshi, who passed away just recently from cancer, after a battle with cancer. He was the exploration manager at Kansanshi, and some of the concepts, the key concepts for structure in particular, came out of field trips and a lot of observations out of Kansanshi that started back in 2008. And James and his team were a big part of supporting that and helping that and part of the conversation at the time. So yeah, there's great work by the SEG looking to set up a fund to support Zambian students in his honour. So encourage you to get in contact with either Mike Christie or Murray Hitzman regarding that if that's something you'd be interested in doing. So title of the talk, so the general talk was, geology of the Copperbelt, but, it was sort of a more, tongue-in-cheek title of salty structures and mineralization. So I'm going to talk about the stuff that really affects mineralogy and then mineralization, which turns out to be salt. And my co-authors, John Basin, Murray Hitzman and Graham Begg, were a big part of the conversation and this work at the time. All right, so what and who? So we're going to look at a snapshot of the Katanga Basin geology, and we're going to focus on the Domes region in northwest Zambia. We'll touch on a metal source, and then just again, so this is just, I'm just the messenger for a whole bunch of collaborative work that occurred from 2008 through 2012 on this topic. All right, so we're going to step back. We're going to start deep and look at some mantle tomography and look at the context of the Copperbelt. So this is a 100 to 175 kilometre depth flight in seismic tomography. And what you can see is the white, the old and cold are the thick cratonic regions. So you see the Congolese craton here, and down here in the sort of composite, what's called the Kalahari craton. The blue are the hot regions. We do actually have the Tanzania craton out here, but it's washed out by the East Africa rift. And just of note is the Copperbelt, right, in the white circle here, is in a suture zone between two cratonic regions. And that's, significance in terms of suture and big crustal and mantle architecture setting. So zooming into Southern Africa, we've got the greater Kalahari craton, which is a composite of other Archean blocks, but we call it the Kalahari craton as an overview, and the Congo craton to the north. In between, Proterozoic mobile belts that separate the two, and the Lophidian portion is right in the center here. We've got the Damara down to the west and the Mozambique out to the east. What's significant is that the Congo craton, the Kalahari craton, has more or less been in this configuration since the assembly of Rodinia, 1 billion years ago. So they've jostled, they've moved apart a little bit here and there, but they've more or less been in this configuration, and that has significance for the Lophidian basin, part of the basin rift up here in the center of the continent there. So zooming in on the Lophidian itself. So this is a oft-site and cited map from Dave Selly et al. 2005, and just really good sort of overview of the distribution of Neoproterozoic metasedimentary rocks in the Katanga, right? And they're broadly divided into 5 domains. So starting from south going to north, we've got the Katanga High, Synclinoria Belt, the Domes region, which is a strongly metamorphosed belt, and then in the what's termed the foreland fold and thrust belt in the Congolese part of the belt, and then up into the actual foreland itself. So we're going to challenge some of those, the terminology and the reason for why those domains are demarcated. In particular, we're going to focus on the Domes region. Long history of deposition, mineralization, and deformation metamorphism. So deposition from 880 to 570, mineralization spanning 300 million years. So very, very long time period of mineralization for one particular basin, and peak thermal event at 550 to 500. So I'm going to make a comment about the Domes region of the basin in general. So the basin, it lacks what I would call steep, like basin-wide penetrative structural elements. So when we sort of you go to different parts of the Katanga Basin, and there's a history that talks about inversion and crustal thickening and shortening and orogenesis and all those things associated with structures, right? And what the remarkable thing you see in the Katanga is a lack of these structures in terms of upright fabrics. You see around the Domes region, there is a widely developed flat fiber fabrics. So these are bedding parallel schistosities, which then drop off really rapidly north and south and up section away from the basement basin contact. Okay, and this has significance. We're going to get into the detail of this later on. There is locally developed upright folds, strong fabrics, but again, they're locally developed and they occur in what I would argue are sort of buttress regions. And we'll get into the significance of that later, but it's just a key message now is that there's a lack of steep, penetrative fabric elements across the basin itself. So a lot of the work was sort of focused on the Trident project area in the Kabompo Dome here, as well as work around Kansanshi in the Domes region. But there's also drawing on a lot of observations from the Petty Congolese Pedicle, Frontier, Lonchi and Dola region over here. But we're going to end up focusing on the Domes, in particular on the Trident area there to the northwest. So another map looking at the geology. So this is a really neat map because what it tells us about is the distribution of salt and the main rift axes and depot centers in the basin. So this part of the rift was it's a failed rift. It's an alaucogen, so we never actually developed oceanic crust. So up in the top part here, up in the Lithilium proper, right, we never actually had rifting, and then it stopped, right, down along the Wembeshi shear zone, and then going out into in Namibia, we've got the matchless belt, which is an amphibolite belt, which is, there's relics of oceanic crust. The key message from this map is that above, north of this sort of feature, up here in the Lithilium, we were closed from open ocean. So there's periodic marine flooding events, right, and incursions, but it actually wasn't ever open to open ocean, right? And just keep it somebody just in a few slides time, we're going to have a look at another map. Have a look at the geometry of the main salt basin here, going through Congo. You can see it's sort of asymmetrically opening and widening to the northwest, and we're going to focus on that in a couple of slides time. So just have a look at the overlay of where those shapes are, because what we're going to look at now in the next slide is basement domains, and those are your reference points for the Katanga Basin there. So this is so they've got the Domes region here, right, as this arcuate belt, and this is the Bangwelu block, right, just to the northeast, right. This is the map of the basement underneath the Neoproterozoic, right. So this is mapping what's underneath, and what's really significant about this is the assembly or the relationship between the Archean blocks and then the different age Proterozoic mobile belts. So if you were to put this, like reassemble this as a jigsaw puzzle, just spot the ages along the mobile belts in the Proterozoic. So we've got an Archean block up here, the Tanzanian Archean craton, and we've got a 1.8 or 2.0 to 1.8 mobile belt between that and the Bangwele block. And we know that this is the Bangwele is reworked Archean, and this docked with the Tanzanian craton between 2.0 and 1.8. Okay, at 1.4, the Gabaran mobile belt. So this mega block here then docked onto the Congolese craton, followed it with the final assembly of Rodinia at 1 billion years, with the Kalahari craton to the south docking onto that. Okay, so you've got a long history there of subduction and crustal reworking. All started from Archean protoliths. And what's really interesting is that in those mobile belts in particular, you've got calc-alkaline subduction signatures in 2.1 to 1.9, and then less so, but still present in 1.4 to 1.0. But in all of the Neoproterozoic rocks, right, the magmatic rocks, there's no, in the Neoproterozoic area in the Katangan, there's no calc-alkaline signature. It's absent. Okay, so what? So why is that significant? Why is that assembly and that calc-alkaline signature significant for us? Okay, what it tells us is we've got a long-lived history of crustal recycling. So from the Archean through several events in the Proterozoic up to the Neoproterozoic, you've got potential for enrichment of lithospheric mantle. So you're looking at potential metal sources as implications. We've got an absence of subduction or oceanic crust formation during the Neoproterozoic. We've already outlined that occurs further to the south. And all these rock associations and even from the basement associations all point to intracontinental processes, right, during deposition, mineralization, and deformation of the Katangan supergroup. Okay, and so that tells us we've got a pretty unique basin in terms of setting. Right, so this is from Graham Begg's work from Minerals Targeting International. And so what this is a map of is, and it's a reconstruction of upper lithospheric domains, right? So this is lithospheric, it's a map of lithospheric mantle blocks. So the sort of blocks that float underneath the crust, right? And what Graham does is he's got a global map of these. Many people will be subscriber to Graham's product, but these are defined using large-scale tomography, gravity, magnetic data, and supported by geochemistry. There's a lot of metadata in the shapes as well that talks about their recycling and reworking. But what he does is, in certain areas, he can actually do reconstruction or movement history of the lithospheric mantle. And he's got one here for the Copperbelt. And what's really neat about this is, so if you look at the timing of this, is Copperbelt from 800 through 600 or so, right? And what it's showing is these suture zones here, right, or these structures are the boundaries of the ULDs, right? So what we're talking about is that block here, right, is one ULD, and there's a series of other ULDs he hasn't put on just because of the confidential nature of his work. But the ones we're focusing on here, they basically moved as they moved south, right? He's basically mapped the movement of them, initiating with the breakup of Rodinia, and they moved asymmetrically. So you get a scissoring effect, right, with the shape of the block and the way this was accommodated along another suture zone. And if you think back to the map that Murray had before in terms of the location of the evaporitic stratigraphy, right? Salt-bearing stratigraphy in yellow, right? This is the exact same geometry. All right, so what Graham's done here is predicted the location of and geometry of maximum rifting in the crust, and has shown us where our evaporitic basins have formed at this rifting time. And also there's big correlations with the ULD boundaries that run through Western Zambia here, and presence of evaporitic stratigraphy. The significant thing about these arrows here, so we're looking at the blue arrows are the movement of the ULDs, and then these yellow arrows show the movement or the flow of the crust as the ULD moves. So these are accommodations. So basically, where the breaks between the ULDs, so there's a break here. So if they move apart, the upper crust flows in to the gap, right? And so by definition, where these two areas of crust are flowing away from each other, this is our zone of maximum rifting. And what we know from geology is also the area of maximum salt deposition and thickness of subbasins in the Congo there. So it's a really, really neat correlation. You know, he's independently predicted the basin architecture from mapping the mantle. And I think it's like a remarkable correlation there. And then during inversion at 550, these blocks moved back from south to north. Graham terms it as an emerging mountain belt. I'd not necessarily agree with that, talking about orogenesis and serious amounts of crustal thickening and uplift. We don't actually have good evidence of that. I'll run through some scenarios later, but they do dock, and there is an inversion of the basin. Down to the south here, we do actually have, below, this is the Wambeshi shear zone. You did have oceanic crust develop, and then that is closed off, and that's your matchless amphibolite belt down through there. So yeah, so we're just gonna move on, and what we're gonna do is talk about the significance of this inversion and what it looked like and how it manifests in Zambia and the domes region, because this ULD boundary here runs right through the domes, right? And so when we're going to show a map of the domes in a few slides, just keep that in mind. So back to our original geology map. So now we've gone large, and now we've got a sense that these domains in the Katangan supergroup, right? They had names before, but now we've actually got processes and reasons for why they are how they are, right? And their arrangements. So they reflect differences in the basement architecture, deformation and metamorphism, and in particular the halokinesis, okay? So volume of salt. So in the Congolese part of the belt, where there is the thickest, that was the zone of maximum rifting and thickest salt deposition, there's a lot of halokinesis, right? And the structural style is very, very different compared to the rest of the basin. So what we're going to do is zoom into this part of the Katangan on the domes. Sorry, before we get to there, we're just going to have a look at, so there's a cross section, is north to south cross section, okay, and this is is also from the 2005 paper of Selly. So one thing to consider about this map is there's lots of upper crustal lateral translation where we've got large scale movements and thrusting, and so even in the Kolwezi clip was thought to be, some people have interpreted movement of 100 kilometers. One thing that we'll say is, based on the lots and lots of field observations in the domes region, we've never seen basement over thrust over Katangan, and certainly haven't seen back thrusting of any type. This sort of geometries here, vertical tectonics and halokinetic type geometries, we certainly see in Congo, and Selly and a few others put out a paper a couple of years ago that went into this in more detail. I think there's been, further work and further observations that support that this sort of vertical salt tectonic style of geometries is much more prevalent and an acceptable way of interpreting the geometries in Congo. I think it's fascinating because as we've learned more, probably the only the most robust part of this whole cross section is this little nose of diapiric Rhone in the Congo. So focusing in on the domes region itself. So we've got the Paleoproterozoic crystalline basement, Rhone sequence. So the stratigraphy is, I'm not going to go into details on the stratigraphy, but it's difference between synrift and then sag phase. Thing to take away from this map is the volume of mafic rocks. Okay, so these are not well represented on most maps. And if you look at the distribution of these, they line up almost exactly with the ULD boundary that Graham Begg has put on from the GLAM map. And what's really interesting about these mafic rocks, they're sort of 760 to 735, MA in age, and they all have juvenile melt characteristics. So they're all from melting of a stenospheric mantle. Okay, so you've got a big crack, right? You've got your directly sourcing mantle and bringing magmas up into the basin, at 765. So it's telling you about the architecture underneath the domes as being, you've got some big connectivity with the mantle there. So zooming in on the dome's geology, okay? So the interesting thing was, like, the stratigraphy has been, there's been lots and lots of focus on the stratigraphy and successions and getting very, very specific and probably unnecessarily so, right? You think about it from a basin point of view and the processes, these are the significant things are, in the Neoproterozoa, you've got synrift sedimentation. So you've got, the very strongly, your red beds series. So there's the Mindola and the Rat. Okay, very strong sub-basin control, hundreds of meters, tens of meters to kilometers in terms of rapid thickness changes, growth faults, relay ramps and transversal structures affecting the way those sediments are deposited and distributed. Then there is, sag phase style. There's still some rifting, still moving a little bit, but it's dominantly sag phase. You've got a lot of evaporites forming, but you still have a strong sub-basin control on the distribution of rocks. So you can have strong facies variations, carbonates going to argillites, as facies equivalents across sub-basin boundaries during this time. And then we've got the grand conglomerate, so Sturtian is a glacial diamictite, and a sort of sag phase blanket stratigraphy above. Okay, and what's really interesting, if I was, back in the sort of 50s, 60s, I'd be looking for, in the DRC, I'd be looking for the mines formation, right? I'd be looking for, Akai mega blocks that have this level of stratigraphy. And if I was in Zambia, I'd be looking for the ore shale, right, around the Zambian Copperbelt as the first reductant. So this is the first instance of reduced lithologies in the stratigraphy. What we know now is that mineralization occurs at multiple levels. There are fluid pathway shortcuts and different architectural arrangements that permit the oxidized copper-bearing brines to travel much higher in the stratigraphy than was previously appreciated. And so that's significant for targeting and discovery and how you consider where you are in the basin and what the target package might be and what it might look like. Significantly around the domes, the Katangan rocks are schistose. Okay, so these are, biotite, muscovite, garnet, right, in the Trident area. And so, so the Kabompo Dome, the Wambeshi Dome, the Swishi, Solwezi Dome, they're all sort of very schistose rocks. Okay, so over the border in Congo, you don't have the same degree of schistosity development, and not as much in the Zambian Copperbelt. It is still there, but it's not as widely developed. And what's really interesting is that schistosity, it is very, very strong metamorphic gradient. So as you go up section away from the basement contact and then away from the domes in plan view, it's on a hundreds of meter scale. You go from a biotite garnet bearing rock to a shale or a mudstone, right, with no schistosity. So there's a, clues here that that these minerals aren't necessarily behaving the way they should in a regional metamorphic sense. Okay, and so we're going to get to that in a minute. So focusing on the Kabompo Dome, so the Paleoproterozoic core. The key note to take home from here is that the Katangan stratigraphy dips away from the dome apex, in all directions. So in here, it dips to the south. Here it dips to the north. Here it dips to the east. Here it dips to the west. Okay, separating the Katangan, right, from the basement is a shear zone, right, 100 meter thick, up to 100 meter thick. It's a biotite phlogopite rock, right, and it has north-directed kinematics. So it's a simple shear zone that separates the Katangan rocks above from the basement below. So what's really neat is if you're mapping up on the northern part of the dome here at the contact, it dips to the north and it appears like a normal fault, right? So because it's dipping down dip shear. Right? If you're here on the south and you're dipping away to the south, it looks like you've got a thrust or a reverse fault, right? Because it still is moving to the north. The key take home is that the sheet of Katangan rock moved northwards over the basement dome. Okay, above that shear zone, The fabrics are dominated by simple pure shear. Sorry, so we've got our shear zone where you've got, movement, we've got very strong mineral lineation, lots of asymmetric kinematic indicators. You go above the shear zone into the package up to grand conglomerate level at least, and you've got pure shear. So when I say pure shear, it's just flattening, so flow in multiple directions. Right, so you've got a combination of sheet of rock moving to the north, but by definition, to have pure shear like this and flow in multiple directions, your sigma 1 is into the earth, right? And by definition, that's extension. Okay, so it's really interesting to think about how that fabric formed, given what we're saying about inversion and timing. Okay. That basal siliciclastic sequence, so the rocks that are in orange there, they've got an intergrown assemblage of talc, kyanite, quartz. All right, so this is previously used as a basis for interpreting very high pressure, low temperature metamorphic conditions around the dome. So if you're in the European Alps and you go up to what is like a metacarbonate rock, you find this assemblage of talc, kyanite, quartz, but that rock has been down between 50 and 70 kilometers into the crust, buried as part of a orogenic event. And so we're going to get into the differences between those, right, and what they look like here. So around the domes, previous workers have interpreted up to 50 kilometers of burial, right, or thrust stacking around the domes to explain these apparent white schist assemblages. And so if you put it into thermocalc and you use the bulk rock composition and the thermodynamic estimates for those minerals, if they're assuming they're co-stable, in the range 650 to 750 degrees at 13 kilobars. So that's eclogite facies metamorphism. That's extreme metamorphism, right? And some of the geometries interpreted to explain what was happening in the domes at that point was we would basically initiate a break and then essentially underthrust the dome stratigraphy 50 kilometers and then exhume it. And then the other one is thrust stacking, right? But we haven't seen, the thrust stacking in particular, I sort of mentioned, we haven't seen evidence for basement being thrust over the Katangan in any location. So the problem with high pressure, low temperature metamorphism in the domes region is that the stratigraphy is intact, north and south away from the domes, right? It's the basin itself is largely intact. It's not significantly inverted. You're talking about a basin that was inverted 550 million years ago, and it sat there since then, and it really hasn't done much. It hasn't been really eroded. If it was significantly inverted in terms of forming a mountain range, right? So orogenesis, you would have a molasse, and you probably wouldn't have a basin left, but it's still there, very, very much intact. A couple of key observations from Trident. We've got 2 kilometers of Katangan stratigraphy where our sequence is consistent over tens and tens of kilometers, right? And we can see sedimentary flame structures in the rocks adjacent to the talc, kyanite, quartz that have supposedly been down 50 kilometers and then exhumed intact. So there's this very improbable scenarios to explain that mineralogy. We have no elevated geotherm. We've got apparent elevated geotherm. So in an eclogite facies terrain, you would depress the geotherm because you're putting cold rock into hot rock. And we've got no real eclogite. So there was interpretations of coronitic reaction halos in metagabbros, which turn out to be just alteration. And there's no omphacite or the other coesite, all the minerals that you need for ultra high pressure metamorphism. So we're left with a conundrum. So that because this affects how you look at the basin and think about where to go from an exploration point of view and just trying to understand the geology. So the key is in the distribution and nature of the talc, kyanite, quartz. So observation 1 is restricted to the basement Katanga interface, right? We don't see it higher up in the stratigraphy. And more importantly, we don't see it in the basement itself, right? It's within a specific stratigraphic level in the Katangan. It's an alteration assemblage to hydrothermal nickel sulfide mineralization at the Enterprise nickel deposit. We've got fluid inclusion analysis of the talc, quartz, kyanite bearing veins, right? We've got fluid temperatures of 330 to 415, and even hotter. Some of the other additional work has put us up to sort of 500 degrees centigrade. But the key there is that you've got up to 40 to 70 weight% sodium chloride equivalent. So you've got hypersaline brines, right? These are really, really salty fluids, all right? And when we look at, I'm going to show you some photos of some rocks, right? But these features suggest a metasomatic origin. So it's a brine alteration process for the talc, quartz, and quinite, and it's not a metamorphic mineral reaction. So look at some photos. So these are from Enterprise. So this is what was a meta siltstone of some sort. The rocks here are extremely, extremely altered. So actually working out what the rocks were to start with, from seeing through, you know, several phases of alteration is really challenging. We had some sort of fine grained meta, you know, siliciclastic rock. You can see original banding that would have been compositional banding, and this is replaced by talc and hematite. Right, the dark mineralogy is specular hematite. Then over the top of that is talc, quartz, and quinite. So this rock here, this white rock, is, if you petrographically, is just talc, quartz, and quinite. And you can see it's coming across as an alteration front, like directly across our compositional banding. Here's turning a black rock into a white rock. This is one of my favorite photos. So here I've got a black shale, right? So this is just like as a muddy rock. And here I've got an alteration front with talc, quartz, quinite, and sulfide. All right, and you can see, you know, you've got fluid pathways in veins where you've got both enabling and locally impeding fluid flow through that rock. But, you know, if you look at this rock, take a thin section from here, take a thin section from here, you wouldn't believe that they were the same rock. And last slide here is good. It's a black shale, right? Kyanite, sulfide altered. Here we've got a vein, right? Kyanite, quartz, talc, nickel sulfide, right? So this mineral, the kyanite and our talc and our quartz, as well as nickel sulfide, is coming out of a hydrothermal solution, right? It tells us we've got mobile aluminium, so we've got a pretty aggressive fluid. And this mineral assemblage is, you know, again, is supporting extreme brine conditions. And so the reason for those thermodynamic estimates don't work is, so above sort of, you know, 15 weight% sodium chloride equivalent, thermocalc falls over. I know there's been recent advances in the way to do, you know, thermodynamic modeling and accounting for extreme brine conditions, but at the time, you know, above 30 weight%, the thermodynamic estimates were irrelevant, right? So, and it brings us back to the source of the salt, which is evaporite. So there's a couple of things going on in this diagram. I'm going to walk through it. And so the question is, can a hot, salty, oxidized acid fluid explain the observed mineral assemblages? Right, so now we've got an oxidized fluid because I've got my hematite, and I say acid because we know from the nickel world that to transport nickel in solution, you need a extremely acidic fluid. And the observation of the presence of talc is talc usually forms in and around carbonates, whereas buffering against carbonate and coming out of solution there. The diagram here shows several things. Okay, we've got the kyanite, andesite, slimonite stability fields. We've got geothermal gradients. All right, we've got metamorphic facies, so eclogite, blue schist, you know, green schist, amphibolite, and we've also got stability fields for metamorphic minerals for a politic composition rock. Okay, so we've got a very, you know, from the thermodynamic work done on the talc, quinite, quartz, this will put us up in this field, right? And it just seems it's highly improbable given the geology that we've seen. The conundrum we've got is that with biotite and garnet, the stability field is around here. So, you know, 4 to 7 kilobars, 450 to 600 degrees centigrade. So in a regional metamorphic setting, you need to bury this package of rock 12 to 22 kilometers, right, to get to these conditions. And what we know from the geology, right, and the other analytical work is that we can't go deeper than this in terms of pressure. We know we've got up to 500 degrees temperature, but probably even shallower crustal setting, right, for the formation of those minerals. So what we're talking about is you know, with an extreme brine, we're getting metamorphic mineral or phase changes and reactions where minerals are forming well out of their, accepted or known stability fields, right, or PT conditions. And so we start, particularly for biotite garnet, right, we've got a set of rocks. These are index minerals for classic metamorphic petrology, and we're sort of questioning, is the classic tenets of metamorphic petrology correct? And it was a really big realization. Like, we actually, we need to do a whole bunch more analytical work, because we've got this set of observations that mean that even for biotite garnet, it's because we've got this extreme brine. Perhaps we're getting a whole bunch of other minerals forming well outside of their accepted or classically known stability fields. And so the term, Murray uses the term hydrothermal metamorphism to explain, the textures and context. And I think it's a really good term to use. And the take-home message from that is the extreme brine conditions, and from a metamorphic point of view, reduce the activity of water, right? And that's the key part of those mineral reactions that matters for why those assemblages are where they are. So let's try and put all this together. So we've got basement architecture, we've got observations of pure shear, simple shear, really strong thermal gradients, hydrothermal fluids, and brine metamorphic, brine metasomatism. So one interpretation, right, taking from, building up from the CELI 2005 work, is a geometry and an architecture similar to a metamorphic core complex, where if you have, SIN 550 to 500 asymmetric extension of the lithosphere, right, you can have your domes going, as positive features. This results in a sigma 1 in the vertical, right, explaining our flat fabrics. North-directed transport of the Katangan sheet as the block of rock moves over in Congo, we get the whole bunch of salt evacuation, and we know that we have this diapiric effect in the Congo. So if you have a lot of salt evacuation, and a big volume change, we're going to have a natural inclination for the whole pile of rock to fall in and try and into the space that's just been accommodated. And so dragging the sheet of rock from south to north. And then, with an elevated geothermal isograd, we know we've got, a stenospheric mantle melts there a little bit earlier, but we do have some really strange intrusions around 550 as well. And essentially along that, detachment surface, which is, ductile shear zone, dissolution of evaporites, then essentially going up, right, to the highest point around the domes. And if, we've drilled on the southern part of on the northern side of the dome, which is a Kansanshi location, and this observation holds true, where you have very low-grade, apparent low-grade metamorphic rocks, and you go into strongly schistose and ductilely deformed rocks. However, it doesn't speak very well to ULDs, and it doesn't talk about the glam reconstruction, which does actually have a component of shortening or inversion. Okay, so it's difficult to sort of reconcile a pure extensional environment in amongst all of that, given that we know that in the Gondwana the blocks docked and moved back towards each other. So really neat thing about Graham's approach is with the movement of the ULDs and the basin, if we take the estimated volume of the basin, so if we got an average thickness and we know the surface area, we can calculate the volume. And so if we back calculate the volume in terms of accommodation space, that translates to how far the crust is extended, right? And that translates to a movement. And so what we can calculate for the extended Katangan Basin is that you've got only 30 kilometers cumulative extension across the entire basin, right? So the two ULD boundaries accommodated the movement, and we've got evidence of, mantle plugs in Graham's model. He has stenospheric mantle plugs to fill the gaps, and under the domes we know we've got a stenospheric mantle mafic rocks, and then in the Congo, based on the forward and potential field modeling of magnetic data, there is evidence of dense mafic rocks quite deep that have never been seen, but that's, that's an interpretation. So what happens when you move those blocks back together, right? So we're only talking about 30 kilometers, right? That's remarkable, right? So you think back to the amount of, hundreds of kilometers of lateral translation, orogenesis, mountain building. We're talking about extreme inversion, crustal thickening, etc. Here we're saying the basin it's moved apart a little bit, and then it just went back, right? And what around the domes region, essentially, it must have been a proto dome in terms of the basin shoulder with respect to the riftings. We know the thickest part of the basin was out here in the Congo, and so that rift shoulder went up, right, in the crust when the two ULD blocks docked and collided, and then out in the Congo main, again, massive salt evacuation, and still permissible for geothermal isograds and magmatism and all the structural observations we see of the Katangan sheet of rock sliding over the domes towards Congo. Right, so that's some big things about architecture and reconstruction of the basin to consider. Now we're going to have a think about metal endowment. Right, and this is really interesting because we've talked about some really aggressive brines, right? Really interesting fluids that are doing different, really interesting things to mineralogies. So if we've got a back of the envelope calculations of the amount of red bed in the Katanga session, it can't account for the amount of copper metal in known deposits. So if you use a classic red bed sediment hosted copper model, we don't actually have enough source rock for the copper that's known. And this was back before Kamoa and Kakula had massive resources, so it's even blown more out of the water. So one consideration is metal from the basement. Right? So with all the crustal Archean reworking, can we have a metal from the basement? And so there's been some work looking at numerical modeling of brines, then account for recycling of dense brines, down into the crust and then coming back up during the inversion. The hafnium isotope data, right? So looking at zircons around the Kabompo dome, right? We can demonstrate input of juvenile mantle melt, right, during 4 crustal melting events prior to the main copper age. Okay, so the zircons are derived from granitoids which have different degrees of juvenile mantle input during emplacement. So is that, with that mantle connection, it's not necessarily a genetic link, but is there an enrichment process there that tells us this is a good area to be in? These are the, from the Trident project area where the samples were taken from. They're basically hard rock metasedimentary samples, one stream sediment sample. So the significant, there's a lot going on in this diagram. Significant thing to look is on the x-axis is age, and then on the left hand, we've got the hafnium isotopes. So what we're interested in is at any specific age where we see a vertical trend, which shows mixing between juvenile, right, and crustal melt inputs during magmatism. And so we've got significant additional juvenile melt at 1.97, 1.9. Again at 1.2, so there's a docking of rhodinia, again at 936, and then 722, 675. So this is the age of our mafic rocks, essentially, right? Again, showing that juvenile melt input. So there could be a link there, but it's really hard to establish a real genetic link between that, from that process through to ore. Or finally, the mantle doesn't matter at all, right? So if we've got a really nifty, unique, hot, aggressive fluid, maybe we can get away with not so good source rocks. Okay, so this map, the geology map, shows in the purples here and the pinks is the basement, right? And this is the sort of basement basin contact around here. And so from several thousands, it was 21,000 soil samples across the Trident project area. We used, so copper scandium is a really good way of mapping areas of enrichment and depletion and where normal mineralogy is expected. So copper and scandium exist in mafic minerals that are a ratio of around 2.5 to 1 in nature. And so where copper has been stripped, right, from a mineral, right, we can say it's depleted, right? And so the dark blue zones there, right, have been depleted in copper with respect to scandium, right, for their given mineralogy. So we're normalizing to rock type and mineralogy here. And so what you're actually mapping, what is mapping is the footprint of our hydrothermal brine fluid, right? So the black dots here are talc, right, and they map more or less the top of the hydrothermal system, and they're buffering strongly against carbonate rocks. Below that, right, in dark blue, we're stripping copper out of rock and taking it into solution. Right? And this is the Sentinel copper deposit. It happens to be where you've dropped a block of rock, a strong reductant, into the oxidized part of the system. Okay, and if you do a mass balance across this, using this area, so on a 50 by 50 kilometers with 500 meters thickness at only 10 ppm Cu, right? So, and that's quite low. Let's look at a granitoid being 40 ppm. We're not going to assume 100% efficiency, but we've got potential to take into solution 30 million tons of copper metal. Right, so you don't need red beds if you have a very, very aggressive fluid taking copper from everywhere. Right, and so Sentinel is 5.2 million tons, and so our question has always been is where is the rest? And what's really interesting is that this footprint, right, this same oxidized hydrothermal brine footprint and attendant mineralogy of talc kyanite quartz plus phlogopite, we've mapped it and geochemically fingerprinted it over an area of at least 400 by 100 kilometers across the dome. So you're talking about true basin scale fluid flow and hydrothermal cells. It's large. And that was all I have to present today. Thank you for your time.
Thank you, Dave, for that. That was a great presentation. I'm sure there are some questions and comments from various people participating. Nolene, do you want to run this session, or shall I MC it for the moment?
I'm happy to, Craig. So if
Okay,
there are any
leave it to you.
questions, let me just turn my video on. If there are any questions, please raise your hand, which you can do by going to participants at the bottom of the screen and clicking on the hand, or just jump right in. Any questions or comments?
Yeah, thank you very much, Dave. It's absolutely brilliant. Gives a whole new perspective on the copper belt. I just wanted to ask you with regards to nickel, because not only do you have nickel in the Trident Sentinel area, but also it's important at Menda, quite heavy concentrations. Yes. And also there's another deposit to the north, which is not on the radar. It's kind of under wraps at the moment, but there is another deposit, a significant amount of nickel, similar to Menda. So how would you relate the occurrence of all grade, if I can use that term, all grade nickel in these environments?
Okay, so I mean, I'll use the comparison between Menda and Enterprise. So Menda sits in carbonate rocks and in a polylithic carbonate matrix breccia. I understand the grades go up to sort of 0.2 as a resource. It's not necessarily high grade, whereas at Enterprise, you've got grades. I mean, the core of the deposit runs between 9 and 18% nickel as sulfide. You've got millerite, vasite, and bravoite as your main mineral species. Menda, I think, has mostly vasite. And the difference is the presence of reductant, right? And so observation, from a mineral system point of view, that hydrothermal, so our brine fluid, right, when it buffers against carbonate, right, you form talc. The talc on a regional scale is elevated in nickel, right? And so nickel is being destabilized at the same time as talc and being sucked into the talc lattice, and that's an acid-base reaction, right? And so where you have that buffering occurring, but where you have a reductant adjacent to that, that physical location, the nickel is able to be complexed into a sulfide, right? And so regionally, we can map anomalous nickel, right, in talc. Enterprise happens to be where you've got preserved very strongly carbonaceous shales, and available as a reductant, right? Once you've destabilized the nickel out of solution through your your acid-base reaction. So there's quite a couple of steps there. But so at Mender, you don't have the reductant, from what I understand. So you've still, you know, you get grade, but you don't get ore grades.
Okay. I'll talk to you privately about it. It's very interesting. Thank you very much.
Sure, no problem.
Any other questions for Dave? Anna?
Hi, Dave. Thanks very much for that. It was a really interesting talk. I had a few questions about the PT estimates for the thermocalc models.
Sure.
You talked about how thermocalc doesn't really cope with these kind of really high salinity conditions.
Well, it didn't. It didn't when we did this, and I understand it's come a long way.
Okay. Well, my question was actually about you mentioned a bit about water activity, and
Yes.
I just wondered if anyone had looked at the effect of water activity on some of those PT estimates, particularly on like the stability field of kyanite, and how if that can be brought down into lower pressures just by looking at variations in water activity.
Yeah, so there was a specific MSc and PhD thesis run at Colorado School of Mines with Corey Mayen was the student under Nigel. Goodness, I've forgotten his last name. That's terrible now. But all, you know, under Murray Hitzman's tutelage, and they specifically looked into those, you know, the analytical work behind, you know, water activity and mineralogy and what that means for PT space. So there are publications and poster summaries of that, and the thesis is available to have a look at. So that has been followed up on, but there is, I'd argue, probably a lot more experimental work to, you know, it's still to get traction as a you know, believable scenario, and if I'm a, you know, pure metamorphic petrologist, there's still a lot more experimental work to be done to pin down water activity levels in a more meaningful way.
Thanks.
No worries.
George, you have a question?
Thanks, Nolene. Thanks for a very good talk, Dave. I'm just a bit puzzled about the salt and the amount of salt that occurs in the Katangan part of the Copperbelt. Do they actually have huge thicknesses of NaCl, KCl, et cetera, salt in the sequence, or is it just mainly carbonates? And something has happened to replace the chlorides and with the carbonates, because I wasn't aware that there was lots of salt in the Copperbelt.
Yeah, so there's there's a lot of magnesium salts. You know, our evidence for sodium chloride is basically by proxy from the fluid inclusion work, because they're gone, right? They dissolved very early on in the you know, as a dissolution series. So if there's some work that if you do the was it crush bromine chloride work on pyrite, you can see an evolution of brines from evaporitic brines, so bittern brines, right, on one axis going through to dissolution brines on another. And so we've got, you know, the very extreme end members of the fluids we're seeing are that, at least indicate, the observation is that probably most of those, you know, the potassium and sodium salts have just gone into solution, and they've passed through the system, and where they are now is a good question.
Thank you.
Kibalo. Oh, sorry about that. Katie, you have a question. David from Leicester.
Thank you, Dave. It's KB here.
Hello. You got me? Yeah, you have. Oh, I've got London behind me. I didn't realise that. Hi, Dave. I like what you did with the copper-scandium ratios there. That was really good. Can you do the same with cobalt, do you know? And can you do the same in terms of scavenging cobalt, or do you need something different in the source or the fluids?
Yeah, that's a really good question. I can see at least in the domes area, you can do the same with nickel. For cobalt, I think there's a slightly different end member association, and I think based on the mineralogy and the associated alteration, it's not as the temperatures are definitely lower and potentially less salty. Okay, but definitely from a temperature point of view, where you're getting cobalt. For most part, you don't seem to have as higher temperatures.
Okay. Okay.
Maybe, do you want to try again?
Yes. Good morning. Thank you, Dave, for
Hi.
that informative presentation. My contribution to your talk is normally, if you look at the Copperbelt type of mineralization, the simple way that you normally explore is the contact between the red base and the gray base, and is mostly consistent along the belt, and is easy spot for most of the explorers. The only challenge is that most of it is sub-economic or uneconomic, or even very difficult to mine. But I'm more interested on your upgrade of those domal structures and overthrusting of what is significant in terms of upgrading mineralization. Because as you know, the source of mineralization is, we don't know much about it, and we don't know if it's enough to come to economic standard. But the overthrusting the domal structures might have some significant in terms of upgrading the deposits. Thank you.
Sure. Okay, so yeah, there's a really good point. So in this basin and in other fertile basins, you can get, at various, there's usually a main redox boundary, sometimes several, and you can get smoke, so trace copper mineralization over very large areas. And so, we've demonstrated that, we can at a minimal distance, 400 by 100 kilometers, track the same fluid. So mineralization doesn't occur across the whole area, right? You get little traces, but you get concentrations and where the concentrations is, so to think about it, one way is for the domes, they do occur as stratigraphic pinch outs, so they were positive topographic features during the time of deposition. So if you've got a thinning, right, of a package that has a fluid in it, you're fluxing, right? You're forcing fluid into a smaller volume and enhancing fluid flux, right? That's one way of getting a greater amount of fluid into a smaller volume of rock. And if that rock happens to be a reductant, you could have potential to form sulfides. And the other one is the sub-basin architecture, which becomes, for my mind, probably the most important thing to look at is where in the Sin Rift architecture have I dropped out a sub-basin low enough so that when the flooding surface comes through, I develop and preserve reductant, right? And so it's the geometry of the basin tells you where it's likely to be and then where it's likely to be preserved. But it's also because of the Sin sedimentary nature of the structures that bound those sub-basins, they're also fluid pathway shortcuts and flux points. So it's those sub-basins that upgrade, they both have a reductant in a greater thickness or a greater quality, and then you also have potential to flux more fluid through that location, leading to ore as opposed to just mineralization.
Okay, thank you.
You're welcome.
Any other questions or comments?
Sorry,
Great,
Dave.
Dave.
Yeah, sorry.
Thanks very much. Go, Bjorn.
Yeah, sorry about that. Yeah, I just had one question related, might be a bit of a semantic thing, related to that hydrothermal metamorphism. Is that the same then as metasomatism? Those PT graphs you showed with the stability fields are generally closed system metamorphic reactions, whereas the textures you showed were more sort of open system, what I would call metasomatism. Yeah.
No, I mean, yeah, and call it, and that's the thing. It's a phrase that we use because we've got it is metasomatism. We can show bulk addition of, in particular, magnesium related to mineralization and ore as a map. You can directly map the metasomatic process and change in bulk composition of the rock. In some places, you still got, you know, biotite garnet, you know, with kyanite, some phlogopite. How much the bulk composition of that rock has changed is way less than the talc-kyanite quartz assemblages, right? But it's still a hydrothermally altered rock, and it's metamorphosed. So you've got to, you know, you're sort of, you know, bordering on the fringes of both terms. The correct term, like you said, would be metasomatism, but it's not, you know, you can't really use it as metamorphism in the truest sense either, because that always speaks to sort of a regional metamorphic processes and, like you said, like closed system components.
Thank you.
No worries.
Any other questions? Sure. As Craig would say, going once, twice, done. Dave, thank you so much for that very, very interesting talk. Everybody else, thank you for joining us yet again. Just like to remind you that we have some talks coming up next week. So on Monday, we have Dr. Julian Verncombe talking about the importance of brownfields gold exploration. And then on Wednesday, Mark Burnett is doing his mentoring talk again, The Road to Leadership. For those that missed it previously, please join us. Please remember you can log your CPD points, but it is informal learning and not part of a formal course. So if there are no other questions or comments, Craig, anything from you?
Nothing from me. I thought it was a brilliant talk. Thank you very much. I understand a lot more about the Copperbelt now.
Good.
Now we just have to get there. Thanks very much, everybody. Have a lovely day further. Thank you. I'm going to end the meeting. Craig, can you end the meeting, please?